Okay, I want to start off with something that isn't in this section because I think it will help you understand the initial idea. I want you to consider this. It's been shown that no matter what piece of paper you find, whether it's toilet paper or adding machine tape, you know what that is? That's what they use to make receipts at the grocery store. They're on big rolls. They put them in the machine, it rattles off your receipt, you know? Those, they come on big rolls like this, or whether it's just a standard sized piece of paper, or whether it's a paper as big as a football field. You can't fold it more than 7 or 8 times. Not just in one direction, in any direction. You cannot fold it more than 7 or 8 times, regardless of the paper that you choose. And the reason why is because if you think about it, when you fold a paper in half, you've cut its length in half, but you've doubled its thickness. You fold it again, you've now cut that half in half, but you've quadrupled its thickness. You fold it 3 times, now you're 8 thick and only 1/8 the size that it started with. So it's getting smaller exponentially as the thickness is getting bigger exponentially, and pretty soon it's too thick to fold. And it's too tiny to make the fold because it's too thick and it's really tiny. Mythbusters wanted to see if they could bust it. They had a piece of paper that I don't know, maybe it was a piece of fabric of some kind, really thin like paper, but they had to have stitched it together. It was as big as a football field. And they tried folding it, and with a machine that compressed each fold, just mashed it down, and then they tried to fold it again and mash it down and see if they could get it to go. They were only able to get about 8 folds. And whether you believe that or not, I don't want you to try it. I want you to just believe me for now because we're going to move on to that. While you can't fold it more than 7 or 8 times, I want you to pretend, this is a mind experiment, I want you to pretend that you could fold it 50 times. The question is, how tall do you think it would be? You think it would be measured in inches if you folded it 50 times?
No.
Feet? Let's take a look and see. It's surprising. It's surprising what can happen here. Look, here's what I'm going to keep track of. I'm going to keep track of the number of folds and the thickness measured in the thickness of a regular piece of paper, a regular piece of typing paper. So this is the number of thicknesses thick. So if I do 0 folds, it's 1 thick. Do you agree? 1 fold, it's twice as thick. 2 thicknesses. 2 folds is 4. 3 folds would make it 8. Got to double it every time you fold. So let's go on down here. What would happen if I folded it 10 times? How thick would it be? Well, let's go back to the top and think about this. There's another way to write these numbers. I'll come back to this one in a minute, but that right there is 2 to the 1. This is 2 to the 2. This is 2 to the 3. And if I come back up here and follow the pattern, this is 2 to the 0, which still fits. Right? So down here, right here, this would be 2 to the 10th. And what is 2 to the 10th? 1,024. 1,024 thicknesses of paper. Anybody have any idea how many papers are in a ream? A ream of paper is that stuff you see in the office that's about this thick that we put in the copy machine. That's a ream. It's R-E-E-M. That's a ream of paper. And I looked it up. It's not approximately. It is 2 inches thick, and it has 500 sheets. So how tall would our folded paper be after the 10th fold?
4 inches.
About 4 inches. A little bit, tiny bit more, because this is 1024. Okay, so let's take this on down and say we could. We can't. We couldn't even do this. But let's say we could fold it 50 times. What would this be?
2 to the 50th.
2 to the 50th. What is 2 to the 50th?
A big number.
A big number. Tell me what it is. I'm going to go up here with it. 2 to the 50th is equal to,
1.1258.
just a minute, 1.125.
899907 to the 15.
Times 10 to the 15th. Thicknesses of paper. Okay, that's a number that's, I mean, that would move this decimal place 15 places to the right and add on about 6 zeros, 6 or 7. It's in the hundreds of trillions.
Wow.
Okay? So to get a feel for that, to get an idea in our minds, something that we're more used to doing, let's see, how many inches would that be? How could we figure out how many inches that is?
Figure out how many inches is on a piece of paper.
First divide it by 500 and figure out how much that's.
Now, don't do this yet, but if you divided it by 500, that would give you how many reams of paper it would be, and each of those is 2 inches. So how about we divide it by 250? Isn't 250 sheets of paper 1 inch if 500 is 2 inches? If we could want to bust it down into the number of inches, every 250 sheets of paper stacked up is an inch. So divide that by 250 and tell me what you get.
4.507.
Just a minute.
503, sorry.
Come on,
503, 599, 6.
Just give me the times 10 to then keep it in your calculator. Times 10 to the 12. Okay, that's still awfully big. That's in the hundreds of billions of inches. What would you like to bust it down to now?
Feet.
Feet, by dividing by 12. Do that.
3.75, 2999, 689. Times 10 to the 11.
Still huge.
Yep.
We're in the tens of billions.
Wait, why'd you?
Oh my.
So make it.
What should we divide by next to get something we can get a handle on? 5,280. That'll tell us what?
How many miles?
Miles.
That's a lot of miles.
71 million miles.
What do you get? 71,
Oh,
71 million miles.
71.
079.
Okay, you're right.
539.
Miles. Anybody know how many miles it is to the sun?
Not that far.
93 million. It's about 85% of the way to the sun. It is within the orbit of Mercury.
That's cool.
Do you believe it?
No.
You should.
That's if you took
Most people don't, but you should believe it. It's the power of exponentials. It's only 50, it's only, and it, paper is hardly worth measuring the thickness of it. You could, it does have a thickness. But 2 to the 50 of those is nearly an astronomical unit. It's in millions of miles tall. Now, shh. This is the thing I want you to get out of this in order to understand the first thing. Well, almost the first thing, not quite. We're going to come back to this idea after I do the first example. But here's the idea. What I want you to realize is that when it was 2 to the 49th, it was only around 35 or 36, between 35 and 36 million. You know, that's still a lot. Well, it's pulled back to within, between Earth's and Venus's orbit, or very close. That's a lot of pullback. And in the 48, that was only in the 20s of millions. So I'm talking about these last couple of folds here, 48, 49, 50. That's where it piled on the paper, right? I mean, and again, after 10, you get into the 25, 30 range. It's piling on miles of paper. But that last fold piled on 35 million miles worth of paper in one fold. You see what I'm saying? And then right at the beginning, right up here at the beginning, when we did 2 to the 10th, it was only 4 inches. We had done 10 folds. It was only 4 inches tall. By the time we got to 50, 71 million miles tall. So you can see as you progress, each fold doubles the one before. And you get up here into these numbers here, that doubling is significant. It's huge. Okay? I want you to come back to that idea in just a few minutes after I show you the method for what we're going to be doing today. And I want you to come back to this notion of folding paper to understand what we're going to develop here. Okay, so first example doesn't have anything to do with what we just talked about. So remember it. We'll come back to it in very shortly. What you're going to use today in a couple of places. Don't panic. Please don't panic, because we're going to use the calculus to develop some things today, and then you're going to use those developments in your exercises. Okay? So don't freak out on me. This idea is called separable differential equations. Sounds scary. It is a little bit. We did it. It's okay. Separable differential equations are ways of integrating or recovering the function whose derivative we're looking at if that derivative involves x's and y's, not just x's. Do you remember that we did implicit differentiation, and when we did that, we also had every time we encountered a y term, we did a dy with it, or dy dx actually, and then we isolated the dy dx terms, factored it out, solved, and usually the thing that we got involved x's and y's. You recall that? Well, so those are derivatives, and we're going to try to recover the functions they came from with this thing called separable variables. Separable differential equation. And this is your first example of one. dy dx equals xy squared. Okay, so our derivative, we've got a derivative. This is called the differential equation, folks, because it's got this differential, and we've dealt with these before. We may not have called them differential equations, but that's what they are. And remember, we can put the dx over here. Do you recall that? Yes. And that's why we call it separating the differentials. But if I just put the dx over here and that's all, I would be trying to recover by integrating dy and the dx with an integral. I would be trying to recover a function written in x and y that's only dx'd. Do you remember that dx has to match the variable that the integral is written in? Then we got problems. This is what you do, folks. Just watch the method. First of all, I'm going to rewrite this as x squared y squared so that I can see that they can be separated. Now, this move right here is called, this is the separation move. You study it before you say, what? Just look at it. This is what I'm going to write next.
Kyle, what is that thing about?
You see how that could happen from there to there? It's that move right there. That's called separating the variables. Can you see that now I've separated them appropriately? Is it separate or separate?
Separate.
E?
Shepherd.
Oh, it's separate.
No, it says A,
Does that look right?
Yes.
Okay. Separate the variables.
I think it's.
I do know how to spell variables, I just don't want to. Okay. All right, listen up. So we separate the variables like this so that on one side it's all y's and on one side it's all x's. And you do it algebraically. I multiplied this side by dx at the same time I divided this side by y squared. Y'all see it? Okay. So now, keep in mind what I'm trying to recover is the function y equals something with an x in it that has this, if possible. That has this as its derivative. That's what I'm trying to do. So the next objective is to integrate both sides to get rid of the dy and the dx because I'm still in differential mode here. If I want to recover the function it came from, I need to integrate both sides. This one with respect to y and this one with respect to x. That's the next step in trying to recover the function whose derivative is this. So coming up here so that you can all see what this really is on the left is y to the -2 dy. I feel like that's the easiest way to write it. This is x squared dx. I haven't done anything there except for rearrange this so that I'm dealing with exponential, the power rule. So what is this one's derivative? I'm sorry. What is this one's integral? My mistake. Negative y to the -1 equals, what is this one's antiderivative?
1/3 x cubed.
1/3 x cubed. What about the c?
Goes on the right side.
Should there have been a c on both of them since they're indefinite integrals? Okay, here's another thing. We're only going to put all the c's together on this side. Don't let that bother you. There was a plus c over here. There was a plus c over here. Both or one or the other or neither of those c's could have been negative. We don't care. We don't know what c is. We don't know what sign it has. We don't know anything about it. I'm just going to dump them all together right there. Because my objective is to solve for y. And if I dump them all together behind the x, I'm getting closer to solving for y. It's just a c. You take one c and combine it with another c, it's still a c. We just don't know what it is. Okay? You what? Okay. Now I have to stop right here because this is super, super, super important. There's one thing I didn't write down at the beginning. It says solve for y if dy dx equals xy squared and y equals 1 when x equals 1. That's an initial condition. Y equals 1 and x equals 1. Why did they tell us this? So that we could find c. It has to go through that point, 1, 1. So right now, right here, at this point right here, we have recovered, well, almost. I haven't quite solved for y yet. But we have found a family of functions that go up and down the y-axis depending on what c is, and we want to pinpoint the one that goes through that point. That's why they gave us the initial condition. Are you with me? Okay. Now, here's the critical part. I even told you the really, really important part. After you have done the integral, immediately after you have done both integrals and get to here, before you do anything else, go find c. Because if you don't, then the algebra that you do along here will affect that c, and you won't be able to just plug it in later. Right here, c has not been impacted by these guys at all yet. It's just a plus c. Find your c right after integrating. Do not wait. You can do it later, but it's much harder. So what we do is we plug in a 1 for both y and x, and what we get is negative and a 1. I'm just writing down the exact details. To the negative 1 equals 1/3 times 1 to the 3rd plus c, and my objective is to solve for c. What is this? Negative 1. Y'all see this negative 1? Yeah? This is 1/1. I mean, it shoves that 1 downstairs, but there's a 1 on top. So it's 1/1 with a negative on it. So it's negative 1 equals 1/3 plus c. If I subtract, I get negative 4/3. You buy that? So now I come back and rewrite this with the c that I've discovered, and I get negative y to the negative 1 equals 1/3 x cubed minus 4/3. I'm still not done with the problem, but I now know what c is. And finding it right here after you integrate is far easier than later. Okay? So now I'm going to come up here. My objective, you got to understand what the objective is. The objective is to solve for y. So for the sake of your being able to see, I'm just going to recopy this. I haven't done a single thing in this step. I'm just recopying it so it's up here where everyone can see. Okay, how could I continue to solve for y? What should I do next?
Combine the terms.
What's that?
Combine the terms.
There's nothing to combine.
You have to put y on the other side, so it doesn't.
You have to leave. We're trying to get y all by itself on the left.
Could we switch the x and the y sides to make y positive?
We could, or we could just distribute a negative through the whole thing, or divide everything by a negative, however you see it. In other words, we could get rid of this next.
Yeah.
Okay, now I'm going to do two things at once. I don't think it'll spook you. This is what I'm going to do. I'm going to write 1/y equals negative 1/3 x cubed plus 4/3. Got rid of the negative and made y to the negative 1/y, because I like positive exponents better. I deal with them better. Okay, and then I'm going to show you a little trick that isn't used hardly ever in algebra, but you can use it, well, get this together. Like that. Then I can just get them over. But it has to be one fraction and one fraction, not two like that. So since these have the same denominator, dump them all over a 3. And so I now have that y is equal to 3, negative 3. I'm using, well, hang on, is equal to negative x cubed plus 4. You can leave it like that. That'd be fine. Or 4 minus x cubed. That's prettier. It's prettier if you put the positive thing in front. I'll take it either way. It doesn't matter. Okay, or not?
Yeah.
That equation's derivative is this, if you finagle it a little bit. Do you want to see?
That was a lot of work.
Do you want to see that the derivative of that gives you this?
Yeah.
You do?
Why not?
Okay.
But how much time was it?
Well, as much time as we need. Do you want to see it? Yeah? Okay. I'll tell you right now what's going on inside me right now. I'm not sure how I'm going to make this work, but I'll make it work. Nobody's ever said yes on this, so. Okay, let's see if we can make it work. We're trying to get back to, I'm going to erase all this stuff. We are trying to get back to this derivative right here. It might work out fine, but I've got a little flutter in my stomach right now. Wondering if it's going to work out. So I'm cleaning off the board so I can do this. I'm keeping this, that result, and see if I can get back to it. So this is what I'm starting with. I'm shooting for that. So I've got y equals 3 over 4 minus x cubed. And I want to find dy dx. Okay, and that's going to be, going to use the quotient rule, or do you want to just, I think I'll go use the quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom. You agree?
Yeah.
Okay, the bottom squared, which gives me positive 9 x squared over 4 minus x cubed. That's what I'm claiming dy dx is. That's not anything.
The square of the bottom.
Square the bottom, right?
Oh, yeah, that's square the
But then
bottom.
you can
Yep,
cancel out
that's square the bottom.
one of the 4 minus x cubed, can't you?
No, because it's times 0.
Oh, got it, yep, okay. Yeah.
So you're saying what I could do is rewrite this as,
No, never mind, I was.
take a look at what we're shooting for. We want an x squared and a y squared, right? Here's an x squared. So I'm going to take that x squared out and say, okay, I've got that piece. What remains is, if you will, hang on here. What remains is 3 over 4 minus x cubed times 3 over 4 minus x cubed. Do you agree with that? And that's y squared. So it wasn't so bad.
I like it.
Equals xy squared. Get you right back to where we started.
It's
Fly by the seat of my pants. I've never done that one before, but nobody ever says, yeah, let's see it.
Wow.
All right, so it worked out. It worked out pretty well. All right. Now, I want you to come back to the idea of the paper folding and the fact that in the next to the last fold, we were only 34 million miles out. I know you only, but it doubled that to 71 million plus something in one fold. Whereas when we were down around when the exponent was 10, it was only increasing it by 4 inches or so. Okay, I'm going to write something up here, and I want to see if with that idea in mind, if you can understand what I'm saying. Dy dx, I'm going to do it clear over here, is equal to some constant times y. Now let's talk about what this means. This is saying the rate at which y changes. Listen carefully. This is a concept you got to get in your head. That's what this means. The rate at which y is changing, that's a rate, is dependent upon how much we have right now times some constant. In the scenario of the paper, however much we have right now times 2 determines the rate at which it's changing in that fold. When we were down around where the exponent was 10, then if, like for example, if I had it folded and I had a stack of paper about 4 inches tall in my fold, so this is all my paper stacked up like this, then in the next fold, it's going to make it only this much bigger. That would be the 11th fold, would make it 8 inches thick. Are you with me? Whereas going from 49 to 50 made it 34 million miles thicker. So what I'm saying is, this is the 2. This is the doubler. This is the constant. We always multiply by 2 every time. But the rate at which the thickness is changing is completely dependent on how much we have right now. Right? Are you with me? So whatever there is right now, and this is, by the way, this is constantly changing. That's a hard thing to hold in your head. That gets 8, then it'll be 16, and go on like that. That amount constantly changes, and we multiply by that constant again, the rate is now twice as much in that fold. The rate at which is changing. Do you see what I'm saying? It is 100% dependent on how much we have right now before we make the next fold. That's the y value. So if that's the case, then what we would like to do is recover the equation y equals something with an x in it from this differential equation, just like we just did. We want to find an equation that says y equals something, not the rate at which y is changing equals something. You following me or not? Trying to recover the y that made this differential equation true. So first thing I'm going to do is separate the variables, and I get this. dy over y equals k dx. Remember that little separation? Now I'm going to integrate. Is it okay if I do that? Yeah, okay. So this is, remember, this is, well, I'm going to rewrite that. It's 1 over y dy k dx, k times dx. What's this thing's integral? It's y to the negative 1. If we take that up 1, it goes y to the 0, and now we're in no man's land. This has its own special integral. What is it? The natural log of
Absolute value of y.
the absolute value of y. Do you agree? And what is the integral of just 1 dx? X. So it's kx. The integral, this integral is just x. Because the derivative of x is 1. Yeah? Plus c. All the c's dumped over there. Okay, so far? Okay. Now, I do not have an initial condition. If I did, I would find out what c is right now, but I don't have an initial condition. So I'm just going to carry the c through. Okay? You treat the c like any other element of the algebra. So now, how do you get, remember, the objective, ultimately the objective is to get at that y. How do I get rid of this? You e it. That e sitting right there, see the e? Raised to this entire side equals the absolute value of what? So, absolute y will be equal to e the kx plus c. No, kx plus c up here. Right?
Wait, what? Yes. Yep.
Okay.
Yeah, but plus your stuff now. We're good. You're good.
Do you remember that y over here, clear over here, that y was the amount that we have, and then we're going to multiply it by this, and that will be the rate at which it's changing right at that instant? Does it make sense to you that in all practical applications, this has got to be positive?
Yeah.
Then I can take this off.
Yes. Yep. See?
Okay. Okay, the next move I'm going to make depends on you remembering this about exponents. If I have, not e, if I have, just forget about that for a minute. It has nothing to do with these x's. If I have x to the m times x to the n, what is that? X to the m plus n. And so if I have a situation like this, I can rewrite it like this if I want to go in that direction. That's what I'm going to do. See what I've got? So this is going to turn, this side over here is going to turn into e to the kx times e to the c. Does that make good sense? Okay, what is, if I take e raised to a constant, what do I get here?
Constant.
Another constant. I'm going to call it a, so that we don't confuse it with the c that we had before, because it's e to the c. That is some new constant. And so this becomes a e to the kx. That's what y equals, right? Okay, now when, what does this look like to you? I mean, have you seen stuff like this before? This is the parent function for all exponentials. Do you recall that? This is the thing that we use over and over and over again. In case of the paper, this is 2. This is the beginning thickness, 1. This is how many times we're going to use this, 50. Doesn't that look like this? This is the beginning amount, this e to the c thing. That's the beginning amount when we start the clock on whatever we're doing. That's how much we start with. And in all science circles, they call that, why not, for the beginning amount of stuff. And we let things grow as a function of time. So I've changed a few variables there to make it look like what usually happens. It's e to some constant times t for time, and sometimes it's in seconds. Sometimes if it's radioactive material that's got a really, really high atomic number, it's in picoseconds, super tiny. Or sometimes it's in millennia. But this is time, and it depends on the context of the question. Okay? This is the constant of either growth or decay. And if this is positive, the thing is growing. If it's negative, the thing is decaying. This is the beginning amount. And we'll either let it grow from here or decay from here. And this is the amount as time goes along. It's constantly changing. So if you have a scenario like folding paper, where the rate at which the rate at which the height is changing is dependent on how much we have right now, then the equation that relates that is this exponential function. So rather than just giving you this and having you run with it like we did in Algebra 2 and Pre-Calc, now you know where it comes from. It comes from this concept that the rate at which the height changes is dependent on how much we have right now. And the result of that solving of the differential equation is this exponential function, which you've been using for a long time. You just haven't known why it works. Now you do. Okay, so the happy thing about these exercises is, now that we've developed the wheel here, you get to use it just the same way you did in Algebra 2 and Pre-Calculus and the problems we'll see for the That is. Let's talk about some continuously compounding interest. I want to tell you one thing first. I'm going to erase all this. We're going to try to remember this. If you don't have this written down or you don't have it in your memory, get it written down before I erase it, because that's going to be your bread and butter for this exercise.
Circle it right there.
It's in a tan box in your book, yeah.
Yep.
So that's, if you need to refer to that because you haven't got it memorized, then you might want to do that. Okay. Does anybody remember the exponential function for when you deposit money in a bank and compound it, say, semi-annually? They're only going to pay you every 6 months. Remember how that works? What that looks like? The amount in your account has to do with the beginning amount, which we call principal, times 1 plus. This holds the value of your principal, and we're going to add on some interest. But it's the interest rate divided by how many times a year you're going to do it. Because this is the annual interest rate. You have to split that up. If they're going to pay you, they wouldn't. But if they were going to pay you 10% annually, they'll only pay you 5% semi-annually. That's why we do that. And it's raised to the NT because T is in years, and this is how many times they will. If you're going to leave your money in the bank for 10 years, then this number will be 20 because they pay you twice a year. That's why this is how many times they're going to pay you over the term, and you have to split the interest rate up into this many pieces. Okay? That's if they compound periodically. Periodically means not every instant. Now, you guys can understand this. If you take the limit as n goes to infinity, meaning they may compound you semi-annually, that's every 6 months. Quarterly would be every 3 months. Monthly would be every 12 times a year. Daily would be 365 times a year. They could pay you every minute. They could pay you every second. They could pay you every picosecond, or they could pay you every instant. That's what this is. You know what I'm saying? And that would be at the limit as n goes to infinity of this is this. That's continuously compounding. So this is periodically, this is every instant. And people, well, how big is an instant? And an instant is that piece of time such that if you divided it in half one more time, it would disappear. You can divide it as many times as you want.
I don't think banks do that.
Every single instant of time. Okay? And you might think that would be a really, really great deal, and it's not that much better. Take a look at example 2. We're not actually going to do this because I feel like you could do the flooding show, but I want you to look at the difference between the two ideas. Look at example 2, please, on page 352. You got to have your eyeballs on this. Here's your situation. Suppose you deposit $800 in an account that pays 6.3% annual interest. That is impossible to get these days. You're lucky to get over 1 or 2%. This is not happening. Okay, but anyway, 6.3% annual interest. How much will you have 8 years later if the interest is compounded continuously, and if the interest is compounded quarterly? So one of them is every 3 months, one of them is every instant. So we use the PERT one that you were just talking about to do the that they've got there. The amount after 8 years is what that's saying. Is 800 principal investment e to the 0.063. I hope you all see where that comes from, times 8. And if you do that, you get 1324.26. If you compound quarterly using the top one, it would be 800 for P, 1 plus 0.063 divided by 4, because it's quarterly, raised to the 4 times 8, 32 times they're going to pay. If you work that out in your calculator, you get 131907. So after 8 years, compounding continuously will pay you $5.19 more over the entire 8 years. So you might think, that would be awesome if I could get this. It's not that awesome. It's a little more. It's not much. It doesn't do it by much. And here's the reason why, folks. Listen, shh. Because using this power by multiplying by n is only slightly better than dividing. Exponents are slightly more powerful than dividing in this situation. And so as n gets bigger here and n gets bigger, this gets tinier and tinier, but this gets bigger a slightly bit faster, which gives you a slight increase over the continuous compounding. It's not much. Okay, ready to move on? You will have to use these formulas. If you haven't written them down, you might want to write them down. They've got the both of them written at the top of page 352, but this one is written over here on the left. Not on circle them, so you can find it again. Or write it down. Okay. How many of you have had lengthy discussions in science about radioactive decay?
Oh, boy.
Some of you? Well, you're about to have another lengthy discussion with me. And if you have anything to contribute, that's fine, if it's pertinent to what we're doing. Okay. As you know, the atomic number of an element is based on the number of protons in its nucleus. The atomic weight is determined by how many protons plus neutrons in its nucleus. So you can have carbon 12, which is stable. It's atomic number 6, isn't it? Carbon?
Yeah.
So it's got 6 protons, and carbon 12, which is the stable version of it, the most common version of it, has 6 neutrons. And they are happy together in the nucleus, and they like each other. Everything's wonderful. You have carbon 14, you now have 2 extra neutrons. It's still carbon because there's still 6 protons. But you now have 8 neutrons, and it gets a little crowded. Chemically speaking, it's not a good situation. It doesn't like that. And so it begins to cast people out of the neighborhood in the form of neutrons and sometimes protons. If it kicks out protons, now you've got another element because you've lost a proton or 2, right? So when things are radioactive, it begins to, it can be chemically determined, but it begins to spew things out of the nucleus. And if it's only neutrons or pieces of neutrons, as I say, in like beta decay, that's just electrons flying out, and the neutrons become protons because they've lost their negative charge, and now you've got more protons than you had before, and now you've changed the element. Or it could be an alpha decay, in which case it's spewing out a helium atom. It spews out 2 neutrons and 2 protons, changes the element. Might be gamma, which is just straight up energy. And things get shifted around in that nucleus, weird things happen. But that's what it's doing, and it's an attempt to throw out enough things out of the nucleus until it likes what's left, and then it says, okay, we'll stay here. We're not going to spew out anymore. Everybody's good, right? That's a very, very elementary explanation, but what I'm thinking of, okay? They want to discuss with you just for a minute, radium-226. This is kind of an important thing as you become adults and begin to own your own homes and stuff like that. You might want to think about this. Okay, just a quick read. When an atom emits some of its mass as radiation, the remainder of the atom reforms. The atom reforms to make an atom of some new element. That's what I was just discussing. This process of radiation and change is radioactive decay. And an element whose atoms go spontaneously through this process is radioactive. Radioactive carbon-14 decays into nitrogen. It completely changes what it is because of the change in protons in its nucleus as it decays. Radium, through a number of intervening radioactive steps, decays into lead. Lead is a stopping point for a lot of things that have an atomic number bigger than lead does. You know, usually you whittle down to lead, it's the most stable thing. Experiments have shown that at any given time, the rate at which a radioactive element decays, measured by the number of nuclei that change their unit, or that change per unit of time. So what I'm saying is if you got a whole bunch of radium and it's radioactive, there's a certain amount of time before you still have the same volume of stuff, but now half of it's turned into something else. And the rest of it's still there. Okay, it's talking about half-life. This rate of change is approximately proportional to the number of radioactive nuclei present. Oh, did you catch that? So let me read that again. The rate, that's a derivative. The rate at which a radioactive element decays is approximately proportional to the number of radioactive nuclei present. Oh, I erased it. The rate at which they spew out stuff is directly related to the number of radioactive nuclei at the moment, kind of like the number of paper folds we've got so far. So it's still related by this same function that we just derived, got resolved. Now, here's an interesting thing. The half-life of a radioactive element is the time required for half of the radioactive nuclei present in the sample to decay to something else. Example 3, which we're about to do, shows the surprising fact that half-life is a constant that depends only on the radioactive substance and not on the number of radioactive nuclei present in the sample. What I'm saying is, if you've got this much carbon-14, it will take the same amount of time for half of it to decay as it would if you had this much carbon-14. It would take the same amount of time for half of that to decay. So it's not dependent on how much you start with. You'll see that in just a minute, yes?
Is this sort of related? So most things, do they decay to lead because the half-life of lead is really, really long?
Half-life of light.
No, half-life of lead is
Oh.
really, really long. Is that
I don't
wrong?
think that lead is radioactive at all. I don't think it has that. I think it's stable.
I think everything has a half-life. It's just really, really long.
I don't believe that. But, okay.
I'm just,
Some things are stable and they stay that way forever. Let me think. You could be right, because we've only been around 4.5 billion years. It could be longer than that, if that's the case, we haven't observed.
I looked at a half-life of lead, 1.4 times 10 to the 17 years.
Okay, something new I learned today, that's good. But for our purposes, it's fairly stable, we'll say.
I agree.
Okay, what we're gonna do now is we're gonna find half-life, but we're gonna do it my way, not his way. I don't like this way, it's cumbersome, and it results in something that I don't think is intuitive. So we're gonna develop the half-life idea, but we're gonna do it my way, so don't look at that.
Yeah.
Okay? So this is the equation that comes from the differential equation we had. This is the one we were using. Y equals Y naught E to the KT. And since we're talking about radioactive decay, we expect this K value to be negative because we're losing stuff. It's decaying. Okay? In other words, the graph of it looks like this. If you start out with this amount, it's going to decay like that instead of exponentially grow like that. That's what happens when you change the sign on K. Okay? I've said K way too many times. Okay. Yeah, say it again. K. All right. So what we want to know is if we can manipulate this for any radioactive substance and see if we can figure out how to find the half-life of it. Well, find the equation that relates it if we know the half-life. How about that? So watch this. And watch what we're going to do there. What we want to know is how long will it take? We're looking for this. How long will it take for this to turn into half of that? So this is the amount that's left after time has elapsed for a while. So I start out with this much. I want to know how long it's going to take before I have half of that. That would be the Y value. Does that make sense? Yeah? E to the KT. So here you can see the very first thing I'm going to do is divide out Y naught. That's why it doesn't matter how much we start with. This amount that we start with is irrelevant. It cancels out. And I have 1/2 equals E to the KT. Remember what we're trying to get at? We're trying to get at the T. How do we get it? How do I get that pulled down?
We're gonna have to natural log that.
We log both sides. Natural log of 1/2 equals KT natural log of E, which is 1. So I'm not going to write it. Y'all following? You've done this before? Do you want me, anybody need convincing of that?
I remember that.
Natural log of E is 1 because it's E base E of E to the 1. They cancel each other out. It's 1. Do you want me to show you that? And so T, the half-life of the substance, is the natural log of 1/2 over this K value. That would be the half-life. You're going, what's the K value? Well, let's do a problem and you'll see. We'll come back to this. Come back to this.
The book says it's L&2 over K.
I know, that's why I wanted to do it my way, not his way, because my way has a half in it, which is what we're talking about. His has a 2, which is counterintuitive.
That's the same for Bill?
Yeah. You'll see in just a minute. If he's saying is the natural log of 2 over K, why would, let's go ahead and discuss that. Why would his say the natural log of 2 over K and mine says the natural log of a half over K? How could they possibly be the same? Because he's taking into account the fact that the K value is negative. If you let K be a positive number, then in a decay situation, this is negative. This would be a negative value. This is positive K, but we put a negative on it because it's decaying. So let's take a look at that. Natural log, let's break down the natural log of a half. Do you remember from properties that that's the natural log of 1 minus the natural log of a half? I mean, the natural log of 2. When you have the log of a quotient, it's the difference of the logs. Do you remember that? It's a property. What's the natural log of 1? 0.
Oh, so you just get that.
Natural log of 2. That's negative natural log of 2. Remember that when another property, if you have a negative 1 right there, that's the natural log of 2 to the negative 1, which is the natural log of a half.
Well, so it's the natural log of a half equal the natural log of 2. They always.
No, they're not equal. One's the opposite of the other. Pretty sure. So the natural log of a half, all I did is took the natural log of a, okay, wait. I gotta go back to here. I forgot where I was going. Go back to here. This is true to here, right? So what I have now is the natural log of 2. The negative natural log of 2 is the same as the natural log of a half. That's what this did. So the natural log of a half on mine right here can be replaced with the negative natural log of 2. And that's over. If he accounts, the author accounts for the negative K value, is what he got. But there's a lot of missing negative stuff there too. And it says the natural log of 2 rather than the natural log of a half. I don't think this to me, when they have a 2 in there, is counterintuitive. You also have to remember that the K has a negative value when this happens, rather than let it have a negative value naturally. I prefer this.
How come
The
that's
K
not
will be negative on its own, and it will develop a negative on its own if it's a decay situation. So what I'm saying is the natural log of a half over a negative number is the same thing as the natural log of 2 over that positive number. You do whatever you want. I like this. And I'm letting K be positive or negative depending on the growth or decay situation. I use this because it has a half in it. If I'm talking about half-life, that causes me it helps me to remember things. We're doing half-lives. This doesn't have a half in it. It's also missing some of the negatives, which can be confusing. Whatever you want. But he comes up with the correct answer. So did I. I like mine better. Okay. All right. So that's the half-life. This T right here, if I replace T with the word half-life, it means the number of years for half of it to disappear. That's a number of years. It's a T value. But you have to know what K is for the particular substance, and K changes from substance to substance. One thing that cannot happen, which is very, very interesting in all the study that we've done with labs and all sorts of things, colliders and all kinds of things that we've built, no one has ever been able to, with heat or pressure or speed, no one has ever been able to change the half-life of a substance. Carbon-14 remains 5,730 years. No matter what you do to carbon-14, the half-life remains the same. At least with the chemistry we know so far. It's kind of cool. It's a constant you can count. For those of you that really, really, really like wild and crazy science, the one thing you count on, the one thing you can't count on, is for time to elapse in a constant way.
What?
Relativity. Okay?
Yeah.
That's right.
Yeah. We're not gonna get there. We're gonna stick with down to earth stuff where time does pass relatively uniformly. Okay, so you might want to get a half-life thing written down, whether you write down his or mine, I don't care, but make sure you have a half-life formula. Okay, I am not going to do this next part, modeling growth with other bases. I'm not doing that. You can do it if you want. Read it on your own if you like. Okay, here we go. Example 4 talks about hornets. I like what he has up there at the top in the column. Hornets are plenty. The hornet population in example 4, which we'll cover in a minute, can grow exponentially for a while, but the ecosystem cannot sustain such growth all summer. The model will eventually become logistic, which you're familiar with, or should be, as we will see in the next section. The whole next section is about logistic curves. Given the right conditions, a bald-faced hornet nest can grow to be bigger than a basketball and house more than 600 workers. In the corner of my house where 3 walls met, the roof underneath the eaves, and 2 walls met right there. They built one a couple of summers ago, and it was probably about as big as a volleyball. And there were hornets all over the place, and I was about ready to beat it down and spray everybody and risk a sting, and maybe more than one, and all that stuff. But a friend of mine said, don't do that. Spray it carefully. Spray it with a mist rather than spraying it with a hard thing, And she said, I'll give you the beekeeper's outfit to do it. But she says, I need you to preserve that nest, but I need you to kill the hornets. It's like 4 or 5 nights in a row. Sprayed that out, and all the hornets left or died. She gave me $100 for that. She came and removed it. Some sort of artwork or something. Natural artwork. I'm going, dang, gosh, those hornets come back. They were great. Everything we did outside, everybody was freaking out. Anyway, that's neither here nor there. Let's know what's happening with this situation. At the beginning of the summer, the population hive of bald-faced hornets, which is actually a wasp, is growing at a rate proportional to its population. What? Do you know what they're telling you there? They're telling you that you can use this to do what we're going to do, because this is the equation that results. This is the equation that results from this statement. It is growing at a rate proportional to its population. That's the y or the dy dt equals kt. Remember that? Sorry, ky. However many we have now, the rate of growth is dependent upon this. So we can use this equation, which we recovered. From a population of 10 on May 1st, the number of hornets grows to 50 in 30 days. Okay, so what have they told us there? According to this formula right here, what things have they given us?
Why not?
They've given us why not, which is what? 10. What else have they given us? T is 30 what? It can be lots of different time units, so make sure you keep track of what it is. What else have they given us?
It grows to 50 in that time.
What?
It grows to 50 in 30 days.
It grows to what?
To 15, 30.
Only 15?
50.
Or 50. What is that 50 in our equation?
Why?
Why? That's what it's grown to. This is how much we have right now. This is how much we started with. This is how much we have after this much time. See? You with me? So this is what we've got in our formula. Then I'm going to write 50 equals 10 e to the k, which I don't know, times 30. So I have only one variable left, k. This is going to be my growth rate for these wasps. So the first thing I do in order to get at k is get rid of this 10 by division. That's the first thing you do, is isolate the exponent. And now we e it. And then we divide. That's the k value for this wasp nest. I don't care what it is. You can calculate it if you want, but I don't care what it is. I'm going to leave it in its exact form to make the prediction they're going to ask me to make and approximate only at the very, very end. But I'm going to use this for k, just like it is. Because the natural log of 5 is irrational. I don't want to know what it is. Then it says, if the growth continues to follow the same model, that's a big if, how many days after May 1st will the population reach 100? So now we come back and we let y be 100, because now we want it to grow to 100. We're still starting at 10. E to the K, and I want to know how much time it takes. Now I'm solving for T. You with me? First thing I do is divide by 10. I get 10. E to the natural log of 5 over 30, T. Now I'm going to log both sides, and if it's okay with you, because you guys are sharp, I'm going to log this side and at the same time divide by this, because when I log this side, it'll be this times T, and I want to divide by that. Is that okay? Yeah? So I'm going to say the natural log of 10 divided by the natural log of 5 over 30 is how much time it will take for that population to reach 100. Now you can calculate. Make sure that you put, look, here's what's going to happen. As soon as you hit a log, it's going to throw down a parenthesis. Make sure you close it where it belongs. Hit your divide sign, open a parenthesis. It'll open another one here when you hit the log. Make sure you close that, divide by 30, and close your big parenthesis. A lot of things to think about. What'd you get?
42.
So only 12 and a little bit more days. The thing went from 50 to 100, the population. It took it 30 days to go from 10 to 50. It will only take it 12 more days to double that to 100. 12 more days. Okay, that's if nothing happens like me coming along with my spray or my shovel. Okay. All right. Now we're going to do an actual I'm going to leave this up here. We're going to do an actual radioactive problem. Carbon-14 dating. You've heard of that, right? Have you?
Every day. For 14 days.
Okay. In the upper atmosphere, there's a lot more carbon-14 than there is down here. But in the upper atmosphere, actually, sorry, I lied about that. There's more carbon-14 up there because radiation from the sun changes carbon-12, which is always flowing around, into carbon-14. The radiation causes that to happen. Makes the thing unstable, wants to decay. Because it's a slightly heavier, a little bit of it drifts down through the atmosphere, even though it's all stirred up by weather and airplanes and all kinds of stuff. But it does drift down, and there's a certain amount of carbon-14 in the atmosphere all the time, and you're constantly breathing it in and eating it in plants that have photosynthesized with it. You're constantly eating it in animals that breathe it in as you eat them. And you have a constant amount of carbon-14 in your body all the time because you're constantly taking it in, and as you know, you're constantly spewing things out. And so there's this recycling thing as long as you're alive. As soon as you're dead, you quit taking things in and spewing things out, and what's in there when you die, that's in your body at the time, that carbon-14, which is unstable, begins to decay. And so if you find an old bone and you want to know how long ago the bone, whatever it is, animal or person or whatever, if you find an old organic piece of stuff and you want to find out how old it is, you take a little teeny tiny slice, you burn it, and you collect with a Geiger counter, very carefully, it's a lot more complex than that. You find out how much carbon-14 is in that bone. And then you do the math. You figure out how old the thing is. We're looking for T. Here is here's the situation. Scientists who use carbon-14 dating use 5700. Most of them use 5730. This guy wants to use 5700. So we'll use his numbers. I'll have 5700 years for its half-life. Find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. Well, how do we know how much was originally present? The answer is, we don't care. Remember, it doesn't depend on how much there was initially. None of this does. The 5,700 years is what we've got to deal with. And that has to do with this right here. This right here, if I want to know the K value that I'm going to plug in right here, because I want to solve for T. T is my variable. I got to figure out what K is. That's where this comes in. If they tell you that the half-life is 5,700 years, then what is K? If you cross-multiply and redivide, K is the natural log of a half over the half-life period. That might be something you want to write down. The K value that belongs in this equation is based on the half-life period, and for carbon-14 is 5,700. So the natural log of a half divided by 5,700 is the K value. And I am not, again, natural log of a half is irrational. I am not going to find out what this is as a decimal. I'm going to leave it like that. So it's not approximated. So now, here we go. We're going to say, this is how much we started with, and we want to know how much time it takes before we have this much of that left. 10%, right? I don't know how much carbon-14 was in this bone when the organic, whatever it was, organism died. I don't know how much was in there, but I want to find out when, because 1/10 of it is left. 10% of the carbon-14 it should have is left. Are you with me there or not? So that's the reason why not's not going to matter at all. And it'll be E to the K, which is the natural log of a half. I'm going to write 0.5 just to save a little space here, up here in this big monster exponent. Divide out the y naughts on both sides. Oh, I'm logging, sorry. I'm logging both sides, sorry, I already did that. So it's natural log of 0.5 over 5,700 t. So it'll be the natural log of 0.1. And by the way, can you tell without doing it, can you tell if this is positive or negative? I'll teach you how to do that in just a minute. This will be divided by this fraction, natural log of 0.5, which needs to be in parentheses, divided by 5,700, which needs parentheses. And that will be how long this thing's been dead, or approximately. Gives a good idea. How much?
8,223.36.
That's good enough. A little more than 8,000 years. That's about as good as you can do. How come this isn't an exact science?
This is asking for 10%.
Because the amount of carbon-14 in the atmosphere varies slightly through the periods. This is based on the carbon-14 that's in our atmosphere now. It may not have been the same amount of carbon-14 this long ago. So it's a guess. It gets you close. Okay, now listen. Shh. The reason why I know this is a negative number and this has to be a negative number is because of what the actual looks like. Looks like this. And it crosses right here at 1. The natural log of 1 is 0. Everything between 0 and 1, that's an open hole between here, has a negative y value, right? So if you are logging a fraction, the result is negative. So this is negative, and this is a negative over a positive. So I have a negative over negative, which gives us a positive result. So we don't need to worry about that.
Wait, what is the number? What is that 8223?
That's how many years this thing's been dead.
So it couldn't be negative anyways, right?
Well, right, but I'm trying to show you that the math never produces a negative that you have to adjust.
That's like zombie years.
Because you're logging a fraction over the log of a fraction, which makes it negative over negative is positive.
Oh, snap.
I guess what I'm saying is, if your answer turns out negative, you better go back and look at your work, because it should turn out positive on its own. Okay, we are almost out of time, and Newton's law of cooling takes quite the discussion, so we'll start there tomorrow.
Yeah.
Do you have any homework? Yes, you do. Get started on this assignment.
Hey, you guys did all that.
42.
You don't have to do 42. It says omit 42.